All right, everybody. Welcome to the final seminar of Krishan Rana, who is going to walk us through his PhD work in the next 45 minutes or so. So this is a formal seminar. As you know, it's the last big step before actually submitting the thesis to the examiners. And we'll have a panel today here with Daniel Quevedo, who is here in the room, who is the panel chair, and Tom Drummond, who is online, joining us from Uni Melbourne. Long-time collaborator from the Center for Robotic Vision. So thanks, Tom, for making the time and joining remotely, and also thanks, Daniel, for being the chair today and on the panel. So as you know, I think you've all seen these seminars. Most of you have. It's a formal thing, so please ask your questions at the end. What we're going to do is I'll hand over to Krishan in a minute. He's going to give us his presentation. Then we'll open the floor for questions from the panel members first, then the audience, everybody here in the room, and also on Zoom can ask questions as well. If you're on Zoom, please keep yourselves muted throughout the talk, and then at the end, when you have a question, you can unmute yourself or raise your hand and we'll keep an eye on Zoom here, or you can ask a question in the chat. All right, with that, I'm looking forward to Krishan's talk on some cool research in reinforcement learning and behavior bias. Please, Krishan, take us away.
Thank you very much, Niko. So hey, everyone. Thank you for attending my seminar, both online and in person. My name is Krishan, and I'll be presenting on my thesis topic, leveraging control priors in deep reinforcement learning for robotics. This work was supervised by Niko and Michael Milford, and with support from ACRV and QCI. So just a quick overview of what I'll be talking about. I'll give an introduction and background to the research problem that we're going to try and solve in this work, and then we'll outline the research problem clearly, and then we'll spend a lot more time on each of our research outcomes before we conclude this presentation. So just to set the scene, when we think about robot control, there are two main methods which come to mind: classical control methods and, more recently, machine learning methods. So classical control methods typically rely on analytical derivations of kinematic or dynamical models of a system with which we can use optimal control methods in order to solve a task. So these systems actually work great in structured environments where we actually get reliable and safe behaviors, given that we analytically define these behaviors, right? We understand how these systems actually work. But however, the models that we use for these systems come with a lot of simplifications and approximations in order to make them mathematically tractable. And this limits them to operate in structured environments. When we move to the real world, which is unstructured, dynamic, and stochastic, these systems tend to fall suboptimal or tend to break down. In contrast, machine learning methods actually allow us to learn these complex behaviors directly through interaction with the environment. So these methods are a lot more data-driven than analytical-driven methods. Right? So reinforcement learning has the potential to enable robots to acquire complex behaviors autonomously in the environment. And just some examples of what robots are actually achieving with reinforcement learning for control in recent years. As you can see here, we've got a robot actually operating in an unstructured environment. This is the everyday robotics robot that's cleaning out cantina tables. We have complex dexterous manipulation of a Rubik's Cube with a humanoid type of hand. And more interestingly, recently is this reinforcement learning has been used to train humanoids to play a game of soccer. So this is a very complex decision-making task, right? It first has to actually learn how to control the whole body of the humanoid, and then learn how to kick, and then actually learn how to coordinate with the teammates in order to score a goal, right? So what is reinforcement learning? So more formally, reinforcement learning is a trial and error control approach, right? It allows us to directly interact with the environment, gain feedback from the environment, and then optimize our control objective. So what we have in a reinforcement learning framework is an agent which can take an action. That action is executed in the environment, and the environment returns a reward and a state, right? And this reward is essentially our specification of the objective. So that one of the big things with reinforcement learning, it allows us to specify the objective and not the solution, which we typically see in classical control methods, right? And then once we've collected this data, at the heart of reinforcement learning is this objective, which is to maximize the cumulative sum of rewards or discounted rewards. So essentially, reinforcement learning is much like how us humans learn, right? We interact with the environment and we get some feedback, and then we use that to optimize our internal control system. Good actions are reinforced. We try to repeat them as often as possible, and bad actions, we suppress them. There are two main methods for reinforcement learning, policy gradient and value-based methods, right? Policy gradient directly optimizes for the objective at heart via the policy, by computing the actual policy gradient of our expected sum of discounted rewards. Once we have that, we can ascend it in order to learn the optimal policy. Value-based methods, on the other hand, indirectly optimize this policy by learning a value function, or in this case, a Q function, which is essentially our estimate of future rewards, right? So in a given state, and I take a particular action, a Q value will tell me what my expected future rewards are, right? And we can essentially estimate that using the Bellman equation of optimality shown here on the bottom right. Once we have that, we can obtain our policy by choosing the action which maximizes this Q. Right? So one of the key discrepancies I want to make clear here is that in on-policy, all the data that's collected in that agent interaction loop has to be collected with the current policy that we're trying to learn pi. In Q learning-based methods, we can actually use an external data source like a behavior policy to collect this data, and then we can optimize the policy in that way. So now the question is, why is reinforcement learning still not widely adapted for real-world robot control? We're actually already seeing that it can solve some of these complexities, these complex tasks in the real world. It's got the capability to solve these complex tasks, so why are we not seeing it being used widely across real-world robotics? There are a few reasons. Firstly, RL agents are trained from scratch, right? They assume no prior knowledge. We just let them run free in the environment. And this results in long training times and unsafe behaviors. So if we remember those soccer-playing humanoids, when they actually start training, we just have them fall on the ground and just wiggle around for a few hours. And after like 3 days of training, then they learn how to control their bodies. And then after that, they can learn how to kick the ball, and then they can learn how to coordinate with their team players. This takes a long time. Just a simple task. Here, we're trying to learn how to stack 2 blocks, right? And just randomly moving your hands around in space, it's very rare to just get 2 blocks stacked on top of one another. So this is a key problem that faces reinforcement learning. Training, collecting this data from the environment is highly sample inefficient. The other thing is that RL agents struggle to generalize when presented with out-of-distribution states, right? So we're training this agent in this environment, but all of a sudden, remember, we mentioned that the real world is dynamic, it's stochastic, there's a lot of changes that are constantly coming. If the agent sees an unknown state, it can act sporadically. These are driven by neural network-based policies, and typically when a neural network hasn't seen a particular input, the output could be sporadic. It could be something that's extrapolated. It could be highly unpredictable. So this essentially limits us to just deploying these on a real robot. So you can just see here how that robot that's being deployed just crashes between 2 walls when it doesn't recognize a particular state. So I mentioned that reinforcement learning is actually a similar way to how us humans actually learn, right? But there's definitely something missing, right? Because as humans, we are highly effective control systems, right? We don't struggle the way a reinforcement learning agent learns. So there's definitely a missing component. So we actually looked at some work in cognitive neuroscience to actually understand what makes us humans different from the way an RL agent actually learns. So one paper that actually, some work that actually stood out to us was that humans constantly draw on prior experience to facilitate learning of new behaviors. And we see that every day, right? Or even if you just watch a baby, after learning to crawl, it learns to walk. And then it evolves to learn to run after that. We don't learn any of these from scratch, right? We constantly evolve from our prior experience. And the other thing that was really interesting was that the human brain actually relies on multiple control systems. We don't just have one, like if we look at a robot, we don't just have a single controller governing behaviors, or we don't have a single RL policy governing behaviors. In the human brain, we have multiple systems that arbitrate through through all these different controllers based on speed, efficiency, safety, or uncertainty. So this actually sparked the thought that how can we actually get some of these things in reinforcement learning, right? And one of the key things that stood out to us was classical controllers. There's been decades of research from the classical control community. Why can't we utilize that as prior experience, as a rich source of prior experience for robotics and reinforcement learning? And the other thing that we noticed is that classical controllers can actually be seen as a separate decision-making entity capable of providing safe and reliable behaviors, right? They come with analytical derivations. We know that they are predictable, and can we maybe exploit this, this safety characteristic of these to facilitate real-world reinforcement learning? So with that, we formulate our research question, which is, how can we effectively repurpose classical controllers to address the limitations of reinforcement learning for robot control? We break this down into 3 core competencies that we want this hybrid system to have. Firstly, it's safety. How can we ensure the safety of this hybrid agent, both during training and real-world deployment? Sample efficiency. How can we utilize these classical controllers to make the training process of an RL agent more sample efficient? And scalability. How can we actually repurpose these controllers to solve a wide range of tasks, right? We don't want just a single controller every time. We don't want to derive a new controller every time we want to facilitate reinforcement learning. How can we actually reuse whatever controllers we already have? So with that, we'll go into research outcome 1, which focuses on the safe real-world deployment of RL agents. So as I mentioned before, training an RL agent in the real world is highly sample inefficient. So one way people circumvent this is the idea of training in simulation and then transferring to the real world. However, generalization across every possible state is hard, right? So we can actually see this robot here, sees an unknown state, and it just collapses, right? Some work have tried to address this by via domain randomization. So expose this agent to as many state variations as possible, hoping that the distribution of states it sees when it's deployed is captured by this randomization during training, right? An alternative way, this was some work done in our lab, is maybe build a real-world simulator, collect data from your real world, build a simulator from it, and then train your agent in that. But one thing you notice is that the real world is dynamic, it's stochastic. You're always bound to see something that you've never seen before, right? You can't build an exhaustive simulator. So then we took another approach and we said, let's try and understand where this policy is failing, right? Rather than trying to expose it to every possible state, let's see where it's failing, and then once we know it's going to fail, maybe we can use that as a proxy to inform our decision making. So essentially what we're getting to is out of distribution detection in RL, right? We're trying to see, have I seen the state before or have I not? And if I have not, what can I do with it? So one of the most obvious ways to do it in reinforcement learning in particular is to look at the temporal difference error. And this is essentially how well can we predict our Q value, right? If we can predict it really well, most probably we've seen that state before, right? If we haven't seen, if we have a very large value, then most probably it's out of distribution. But we tested this out in practice and it's a very noisy signal, right? It's a very noisy signal to use for decision making. An alternative is this idea of case-based reasoning, where you sort of cluster similar seen states together and in this Voronoi diagram. And then during deployment, you'll get a new state action pair and you'll look at its Euclidean distance or some distance metric to each of these clusters, right? But this doesn't scale well when we look at continuous action spaces. Right? More interestingly was some work done from the supervised learning community at the time, where they essentially were looking at uncertainty extraction from neural networks. And one of the key things here was that reinforcement learning was moving towards using neural networks as their policies. So it was a really nice step to try out in reinforcement learning. And at the time, we tried out Monte Carlo dropout, which essentially drops weights randomly during inference. And by passing an input through this network multiple times, we can build a distribution over our actions. And we found this actually worked really well. So with that, we actually settled with this uncertainty-based extraction method for an RL policy, and we've got a method to now identify these out-of-distribution states. So now the question is, how can we use this uncertainty to ensure reliable deployment, right? And we already mentioned that we've got access to classical controllers which actually operate reliably, right? So can we maybe use those as risk-averse failovers? So in order to do that, we had to closely couple a classical controller and a reinforcement learning agent. And at the time, concurrent work where I had proposed this architecture called the residual reinforcement learning framework, where instead of learning RL policy from the ground up, we learn a residual to modify an existing controller, right? So you essentially simplify your task to just learning a small delta on an existing controller. So we essentially trained our policy in this manner, and we combined it with this uncertainty-based switch between the two, right? So now we have this ability to essentially incorporate the residual policy or suppress it based off our uncertainty. If it's above a threshold, we turn it off. If it's below that threshold, we gain the benefit of a RL learned component. So bear in mind that the reason we want this RL learned component is it's able to close the performance gap of a classical controller. Typically, these classical controllers are suboptimal, so maybe the reinforcement learning can close the gap. But when we're uncertain, we don't want to use this RL agent. We don't know what it's going to do. Right? So we actually trained that policy in that way, and we tested this out on the point goal navigation task, which was proposed by Anderson et al., which essentially requires an agent to navigate to a goal while avoiding obstacles. So we looked at what classical controllers were out there that we could actually build up one, right? And the most popular one that we found was artificial potential fields, which essentially allows us to navigate reactively in an environment. But we found a few limitations with it. First of all, these systems actually lack the maneuverability in cluttered environments, right? And the other thing is they're prone to oscillations, and they typically get stuck in local minima. So as you can see in this video here, we're just moving down a narrow corridor, and you actually see this high oscillatory behavior of the agent. So, but can we actually still, but the one thing that we did notice is it's a reliable system, right? So can we actually use this? So we trained our system and we deployed it on a real robot. So this was trained entirely in this simulation environment, very simple simulation environment, but we were able to directly deploy it on this real robot. And one thing you notice is with the prior controller, it oscillates along narrow corridors, but by combining the residual, we can see it actually dampens these oscillations and it learns to overcome that suboptimality, and we can continue deployment. We actually see that it also learns some complex dexterous maneuvers in order to navigate in the real world. So over here, it's trying to move through a tight gap, and you can see the robot actually reverses, positions itself, and then moves forward. This is something you wouldn't see from a simple artificial potential fields controller. And over here, you can see it gets stuck, it's a bit laggy. It gets stuck here, and then it reverses out of this local minima and then continues to move. We combine this into a long-range navigation task and to see how it does when it's deployed through a lab where there's people walking around and obstacles just laid around. And what we notice is we can actually successfully navigate throughout this environment. One thing to just notice, to bear in mind here, is that this is an RL policy that's deployed on a real robot without any sporadic behavior, right? And this is an environment it never saw before. It was entirely trained in simulation. So across all these tasks, the classical controller completes the task with high oscillatory motion. So you can actually see that in this bit here. The end-to-end policy typically failed to navigate around corners. So this is typically where there could have been some state that it didn't know. So it just started to reverse or crashed into the wall. And then our system has the ability to actually switch to the policy component, to the classical controller when there was high uncertainty. So it's able to get past these systems. So this work was published at ICRA in 2022 under the title Residual Reactive Navigation. So in conclusion, we addressed the safety component for real-world deployment, right? That was one of our key criteria, and we utilize uncertainty estimation techniques to better understand when an RL agent is going to fail. And then we leverage classical controllers as risk-averse failovers for continual and safe real-world deployment. Okay, so we move to research outcome 2, which focuses on the training side of things. So in this one here, we're looking at guided exploration in unknown environments, but particularly how can we actually accelerate learning with these classical controls. So firstly, just to set the scene for the current state of exploration in reinforcement learning, it's typically random. It's typically exhaustive, right? So random exploration, there's the smart exploration methods. They try to cover as much of the state action space as possible in the hope that once we cover every possible state action pair, we'll be able to identify the optimal policy, right? And they typically assume that we have no knowledge about how the task should be solved, right? So that's why you want to exhaustively explore every possible state action pair, and then you identify this optimal policy. But in robotics, that's not the case. We typically know how to solve a task. We have controllers. We actually have intuition how a robot should act to grasp an object. It's not a completely unknown way to solve the task, right? So can we use this intuition? Can we use this intuition that, okay, we know how to solve a task? Can we use this knowledge to actually bias the exploration process? And this is actually well suited for off-policy RL algorithms. We can actually use these classical controllers as behavior policies for data collection, right? But there are a few considerations that we have to make when using these classical controllers for exploration. One is that these classical controllers are not necessarily the optimal policy. So if we just mimic their behaviors, if we use them for data collection, we may end up just with a suboptimal RL policy. So typically here, this is like the deterministic behavior we get from a classical controller, and this orange line here would be the optimal policy. We may not ever explore that optimal trajectory. And the other thing to note is that off-policy algorithms aren't truly off-policy. You can't just use a behavior policy on an external system from your current policy to collect data in the environment, right? And this comes as a result of this mismatch between a behavior policy and your current policy. And this was shown by Fujimoto et al., where if you just use a data set of external experience coming from somewhere else to train an RL agent, it actually fails. And this comes as a result of the way our off-policy agent is updated using a bootstrapped Q estimate, right? So we have this max operator here, which is actually chosen by our current policy, right? But remember, we've never collected any data with our current policy, so that action may have never been executed. So therefore, we have a Q estimate of something that we've never seen. So most probably it's actually incorrect. But now we're going to use that to update our policy. So this error just back propagates through our entire network, and then it just gets worse from there, right? So you need to balance the exploration between these two systems. So for that first part where we talk about the suboptimality of the classical controller, we make this assumption that the optimal policy actually lies within a trust region of the deterministic trajectory produced by the classical controller, right? So maybe if we explore a bit further away from the classical controller, we might be able to, within this trust region, we might be able to identify the optimal policy. Right? So with those ideas in mind, we propose this multiplicative controller fusion architecture, where we essentially formulate our classical controller as a distribution over actions, right? And this was a very naive way that we did it, where we just attached a standard deviation to the deterministic action coming from the classical controller. But essentially, this formed a sort of a sampling distribution that we could get actions for exploration. And then to address this balance between the policy and the classical controller during exploration, we introduced this gating function. This gating function ensures that we transition at the start of training, we want the guidance of the classical controller, right? And then as training progresses, we want to switch over to the policy, and this will allow it to correct for any inconsistencies in the Q value estimate, right? So over the course of training, during the start of training, our sampling distribution is this combined one. We sample from the classical controller distribution. And then with the gating function, we gradually transfer over to sampling from the policy distribution. So this gating function actually forms a curriculum for the learning agent, right? We have this guidance, and we slowly anneal the classical controller out of the system. So we tested this out, and this is just, if you have a look at this, if you think about the state space coverage that I showed before, we had this, this was after 7 hours of training. We had the agent barely even exploring past half of the navigation environment. Whereas at this stage here, within a few hours of training, we already have a lot of positive bias towards the goal, right? So this classical controller gives us some intuition of how this task is solved, and we can use that to bias us towards solving the goal. At the same time, note how that stochastic variant of the classical controller allows us to explore surrounding regions, right? The hope is that in the surrounding regions, we get some we can identify the optimal policy. So in terms of training, we accelerate learning and outperform all of our baselines. So the blue line, the lower it is, the better, because we were looking at episode length instead of rewards. But you can see that MCF actually outperforms all of them in terms of final performance. But at the same time, we actually have the lowest variance. So across all of these other ones with high variance, they have naive strategies of balancing the exploration between the policy and the classical controller. Whereas with our one, you can see that once we transfer all the control to the policy, we can correct for any of that inconsistency. So this was published at IROS under the title Multiplicative Controller Fusion in 2020. So in conclusion, this work sort of makes progress towards addressing the sample inefficiency of reinforcement learning training by using classical controllers to guide exploration. We utilize distributional output from the classical controller, which serve as a meaningful exploration policy, and we gradually transfer control from the classical controller to the current policy during exploration, which forms a smooth curriculum during learning. Okay, so that was one part of the learning phase, right? We're looking at addressing the sample inefficiency, right? But one other thing is when we want to train an RL agent in the real world, we also have to consider the safety, right? We can't have the agent just ramming into walls, especially if you think about the hardware of the RL agent. This could be highly detrimental to it. So how can we start considering the safety? Right. So one of the things we noticed in the multiplicative controller fusion architecture was that at the start of training, the guidance from the controller provided a soft constraint on safety. Right. We had this classical controller actually biasing us towards meaningful regions of the search space. Right? But once the gating function transferred control over to the policy was on its own. If it's entered an unknown region, it never had any guidance from this. It didn't have the ability to fall back to the classical controller, right? So the part that we want to try and, if we're thinking about safety, we're trying to adjust this here, right? Can we maybe have a smarter gating function that can actually transfer between the two based off when the policy knows that it's in an unsafe, it doesn't know what to do, or it's in an unsafe scenario, right? So to do that, we looked at this and we saw, okay, we've got two distributional outputs coming from the policy, one from the policy and one from the classical controller. If these distributional outputs actually capture the uncertainty of acting, right, the uncertainty of each of these systems for acting, and in a Bayesian context, if we actually fuse these two distributions, we should get the ability to bias towards the most confident one during deployment, right? So we actually looked at these two distributions as independent estimates of the same variable, which was our action, right? And assuming a uniform prior in a Bayesian context, we can actually fuse these two distributions, which actually simplifies down to a very simple normalized product of these two distributions. But we get this nice characteristics, right? If they capture the uncertainty, we can interpolate between the two controllers based on which one is more certain. So we combine these ideas into this new framework, which we term Bayesian controller fusion, which essentially allows us to have a distributional output that can reactively adapt based off the uncertainty of the system. So to do that, we have to extract an uncertainty aware policy. And in this case, because we're focusing on distributional outputs, we utilize ensembles instead of dropout, and we found that this worked better. This was some work that was, again, from the supervised learning literature. Lakshmi Narayan et al., who proposed a way to combine these distributional outputs. And then from the classical controller, we were trying to figure out how to actually extract uncertainty from a classical controller. And one interesting way that we found was that the most pertinent source of uncertainty in a classical controller is actually the sensor. Right? So we decided, let's propagate any sensor uncertainty through to the action space. And we did that using Monte Carlo sampling with the sensor noise model through our classical controller, right? So now we have these two distributional outputs, right? And we tested this out. So what we did as a naive test was actually train this policy to convergence in a known environment where it actually now starts to completely rely on the policy. The policy was the most confident system, but then all of a sudden we just throw it into a completely unseen environment. And what you actually see is the uncertainty firstly behaves how we expected. The uncertainty starts to peak, and as the uncertainty peaks, the behavior system actually starts to fall down to the performance of the control prior. So we don't see it crashing down to zero like you typically see in an RL agent. We actually fall down to the risk-averse, reliable behaviors of a classical controller from which we build up our learning capabilities again, right? So in this constraint test here, we just wanted to see how the system actually performed. Across all of these, we marked any collisions that occurred during this exploratory process, and we see that BCF actually completely avoids these and all these other ones, all these other baseline methods actually still collide. One thing I wanted to make clear here is that our approach is a soft constraint on safety. We're not imposing a hard constraint, because a hard constraint, typically there's a trade-off between safety and optimality, right? You're trying to say be as safe as possible, so don't bother trying to be risky, right? In our case, we sort of leave it, we keep it as a distributional output, and we focus on this exploration within a Gaussian distribution, but with the bias, with some positive bias from a classical controller, right? And we found that this doesn't cripple us in a way that a hard constraint would do. As you can see in this KL regularized method, which is typically a hard constraint, you can actually see the amount of exploration is really focused around the deterministic behavior, right? So one thing we noticed over the course of training, at the start of training, the policy is uninitialized. It's very uncertain, right? So naturally, when you combine these two systems, we bias very strongly towards the classical controller, right? The policy is highly uncertain. And then as training progresses, the policy becomes more and more certain, and then it starts to dominate control, right? So the composite policy biases towards the policy. And what you should notice is that this is actually similar to the behavior of our gating function. So this formulation allows us to actually gain the benefit of accelerated learning, and across all these baselines, we actually outperform them in terms of asymptotic performance to the optimal policy. And one thing to actually even notice is that we outperform residual RL, which learns a small delta, because we're no longer just limiting it to learn a small delta. We're allowing it to learn a complete policy. So it's highly expressive compared to these alternatives, right? And then we notice that we have two systems, two independent systems, and we have uncertainty governing their behavior. So we notice that we can directly deploy this in the real world. So we put this on a real robot, we deployed it on our navigation task, and as you can see, typically it was the corners that was the failure case when we trained in our simulation environment. When we're highly uncertain, the composite policy actually biased towards the control prior. So the control prior gets us through those regions. And then when we actually are certain, we bias closer to the policy. So we gain the dexterous, the learned behaviors that an RL policy can give us. We then also did this we tried this out on a different domain. In this case, it was reaching with maximum manipulability, some of the work that Jesse has been doing. And we wanted to see if our RL agent could actually learn to improve manipulability of just a simple reacher controller. At the same time, can we actually fall back to the classical controller when we were uncertain? So in known goals here, you can actually see that BCF copies the same performance of an end-to-end policy, right? So BCF, this combination doesn't cripple us from attaining the optimal behaviors that a end-to-end SAC policy would attain. Whereas when we're in out of distribution states, what we actually see, so SAC just curls up. I think that's quite dangerous, or it hits its joint limits. But what you can see is that BCF actually mimics the same behaviors of the control prior, right? So we haven't done anything. It's just completely governed by the uncertainty, right? Which is really nice. We can actually now deploy a system without worrying about maybe stopping it or having a human in the loop. So this work was published at a NeurIPS workshop in 2021. This focused more on the deployment side of things, and then we tied this into a larger journal paper, which is currently under review for IJRR. So in conclusion, we actually address two things, right? Sample efficiency, the sample inefficiency of RL by guiding the agent using this composition of the two policies, as well as the safety in both training and deployment. I think that was the key thing. We now address it in both. In the last one, we just looked at it in deployment, right? So we impose a soft safety constraint, which allows us to do this, and this hybrid policy can be directly deployed in the real world for reliable operation. Okay, so now the last thing, how many days time? Sorry. So the last part that I actually want to focus on is some recent work that we did is how can we actually scale hybrid learning, right? So typically, as you've seen up to this stage, we had to have a task-specific controller designed for a particular task, and then we all use RL to essentially facilitate learning of that specific task. So does this mean that every time we want to learn a new task, do we need a new controller? Do we have to design a controller? And in some cases, we may not be able to design a classical controller in that case, right? So how can we actually repurpose classical controllers to actually solve a wide range of unseen tasks? So maybe we don't have a classical controller anymore, but can we still repurpose what we do have, right? And the answer is actually yes, right? But we actually have to view these classical controllers from a different perspective. So typically what we've been doing is we've been looking at this from a complete trajectory view, where this trajectory is actually task specific. It's essentially designed, it's optimized to solve a particular task. But if we look at it from a different perspective, where we actually chop this trajectory up into shorter horizon behaviors, we realize that these behaviors actually consist of task agnostic behaviors, right? These shorter horizon sequence of actions actually consist of task agnostic behaviors. And we actually term these skills, right? So skill is a temporal sequence of actions that represent useful behaviors, right? So if we think about, let's think about a robot arm that's reaching out to pick a block, right? I've got that controller designed to go and pick a block. But if we look at it from a skill perspective, I have the ability to move the arm forward, move the arm left, move the arm down, grasp, right? And if I now want to learn the task of opening a window, it's the same primitives, right? Move the arm forward, grasp, move down, right? So we're just recomposing these behaviors in a different way, even though that classical controller was never designed for that particular task. So this is what we're doing this work, right? We run a classical controller multiple times, collect a complete trajectory, and decompose it into skills. So now we have a database of task-agnostic skills, which we can reuse for reinforcement learning. So the question now is, okay, so you've got a task-agnostic variant of your classical controllers. How can you use them in the reinforcement learning framework, right? And what we actually figured was we can actually utilize these skills as a new action space for our RL agent. So typically, if we have a look at the standard action space of an RL agent, it's actually operating at a muscle twitch level, right? We're actually moving each of the joints at a very small amount, just randomly, and trying to and hoping that we can manipulate these blocks on the table. But a more intuitive way is to actually explore from a set of skills, right? Skills are actually more graceful. They're actually extracted from meaningful behaviors from a classical controller. And if we have a large database, let's try and explore from those set of skills and learn how to appropriately recompose them to solve a new task, right? So we're moving towards a more structured action space to accelerate reinforcement learning. Right? So to do that, we're moving away from a standard Markov decision process to a semi-Markov decision process, where our action is no longer just a single atomic action step, but it's actually a temporal sequence of these actions. Right? So the question now here is, how do you actually formulate this action space, right? You want your RL agent to utilize this action space, you want to sample from it, and the way we do this is we embed these skills into a continuous latent space. Right? So we do this using a variational autoencoder, which takes our sequence of actions, embeds them into a latent space Z, which we can sample and reconstruct into that same sequence of actions. Right? But there's a small discrepancy that we've got from the standard VAE architecture. We formulate this as a closed loop decoding of actions. The reason why this was important was if there were any dynamical changes when executing a skill, we can actually adapt to them, right? You don't want to blindly execute a move left action, right? Maybe I'm moving and there's an obstacle, you want to be able to adapt to that. So we have that ability now with a closed loop, decoder. When I mean closed loop is essentially we're giving it the state every time we decode it. And then the other component to this loss is essentially regularization towards a fixed prior. In our case, the prior was essentially a standard normal distribution, and this prior forms the distribution from which we can sample the embedded skills. Right? So now we've got our skill space, right? So our skill space has all these different skills embedded into it, and we can sample them from our fixed distribution, and we can get some meaningful behavior. So what we got now is, if we're just randomly exploring, we're now exploring in skill space, right? So you can actually see these behaviors are no longer just randomly waving the arm all over space. We're actually constrained towards the table, towards the blocks, which are the meaningful parts of the task, right? But one thing, there's a few things that we noticed, right? The skill space is expansive. It encodes a vast range of skills that could not be, of which some of them may not be pertinent for exploration. So let's actually just think about this a bit more, and the way us humans actually explore when we're learning a new thing, right? I'm chopping a carrot. I'll reduce my exploration, if I'm learning how to chop a carrot, to cutting behaviors, to moving my hand, trying to hold, trying to grasp. I'm not randomly going to try and kick a ball. right? That's a completely different skill set. So when I'm exploring why can an RL agent actually learn in that way, right? It looks at what's in front of it. Oh, there's 2 blocks. Maybe let me limit my behaviors to pushing the block and lifting the block rather than moving away from it, right? So can we constrain our exploration towards meaningful skills? So essentially what we want to go from is essentially, what we've already gone from is moving randomly in space, muscle twitching or joint or motor twitching, to something a bit more structured like this entire skill space, but something a bit more structured which is actually state conditioned, right? We limit our exploration of skills towards only those skills that are relevant, and that's this little red region that we want to sample from. So how can we do that? Right? So we've got our skill space. In order to learn that, what we propose is to actually learn this complex density of the state conditioned skill space, right? And we do this using normalizing flows, which essentially allows us to learn this multimodal distribution by warping a sample coming from a simple distribution into this complex distribution, right? So what we actually get now is essentially the ability to sample from this region here. So we've got our encoded and our broader encoded skill space, but now during sampling we can essentially actually warp our samples towards sampling from this red region. So to put this in perspective, this is an actual T-SNE visualization of the way skills are distributed in the space. And as you can, one thing you can notice is the yellow is the embedded skills, right? And one thing I want you guys to notice is how multimodal the space is, right? So the skills are distributed all over the space. Just randomly sampling from the whole space would result in us actually drawing samples from this blue region where there may not be any skills at all, or even, as we already discussed, some skills may not be relevant to our given state. And with our actual, with the actual prior that we learned, which is shown by the green, we actually can sample from the meaningful regions where there are embeddings, right? So you can see the overlap between the green and the yellow. Okay, so we found that we can actually learn this completely end to end. So we can do the encoding of the embedding of the skills, and then we can also learn this prior over this. And one thing we just do is we just don't allow any gradients to flow from the skill prior into the skill encoder. So with that, we actually now have a more constrained exploration space, which is relevant to the given state. So as you can see here now, we have a lot more behaviors that are actually manipulating the blocks, right? It's no longer just moving around the table, which says that, okay, there are blocks in front of me. Let me try to pick it up. Let me try to push it. Let me try to do different behaviors, right? And that's where the multimodality comes in. You want to try a pushing behavior, try a pick behavior, try a flip behavior, whatever you may have got, right? And the hope is now it'll be a lot quicker to actually try and stack these 2 blocks, right? So now we actually want to think about how can we incorporate this in the reinforcement learning framework. And the way we do that is essentially to learn a high-level policy over these skills. So we're no longer learning a policy that's at the atomic action scale. We're now learning a high-level policy which chooses a skill and executes that for the horizon of the skill, right? So this is the idea for a hierarchical RL agent using the skill space. So we have a skill, it gets warped into that meaningful red region using our flow model, and then we decode that, so we execute that on the robot for 10 steps, and then we choose another skill, right? But there was a problem we found here. So the skill space, we've essentially redefined our action space, right? So we've essentially told the robot that you can choose only from this set of skills. But what if our downstream task doesn't encode some of the skills that we need, right? What if I needed to move my arm higher than a certain height? If that skill wasn't there, we've actually crippled our agent instead of helping it, right? So how can we add this expressivity back into the system? So we introduce a low-level residual policy that can now adapt these skills at the atomic action level. So we've got this high-level policy that's in charge of skill composition, like, right, move forward, move left, grasp. But then we've got this residual policy which can actually adapt our grasp to new objects, to changes in the dynamics of the environment, and essentially brings back the expressivity to this skill-based reinforcement learning framework. So what we did is we tested this out on 3 different environments. Each of these environments are different from our data collection environment. So our classical controller was literally only using, was exposed to an empty table where we just had one controller that just could move the blocks around, right? And now what we introduced in these downstream tasks is some variations to what the agent saw in that data collection environment. In slippery push, we changed the friction of the table, so the block actually moves a lot faster when it's trying to manipulate it, so it's never seen that. In this one here, this tray here actually acts as an obstacle that the agent has never seen, so it actually gets stuck when it wants to move around the table. And then in pyramid stack, we've made a bigger blue block that's higher than the robot has ever moved in data collection, so it has to learn to move above that and stack the blue block. So one thing to notice is across all tasks, we actually accelerate learning using our skill state condition seal space, right? So we actually learn faster than all of them. But actually, more importantly, with our residual, we actually attain the highest performance, right? All these classical skill-based methods can't adapt to task variations. They're limited to their skill space, but we add that expressivity back with the residual, right? So we actually outperform all of them in terms of performance level. In terms of the highest reward attainable. So just to visual depiction of this, as you can see, without the residual, the agent actually struggles to move above the tray. So it's a very simple thing that you think, but remember, we've changed the whole action space. It doesn't have that ability, so it just gets stuck. It can grasp it, but it gets stuck, right? Over here, it's still, again, similar case. It struggles to lift above that block. And with the slippery push, it struggles to achieve fine-grained motion to try and nudge the block to the goal. Whereas with the residual, you can actually see the robot picks it up and actually can solve the task perfectly. So this work was submitted last week to the Conference on Robot Learning Coral under the title Residual Skill Policies, and is currently under review. So in conclusion, this body of work actually tries to address all three criteria that we stipulated, right? Firstly is the sample efficiency. With the skill space, we're now exploring through meaningful behaviors. So we already have this prior knowledge coming from classical controllers to bias our action space. When it comes to safety, we've moved away from just random dithering of our joints to something that's a bit more graceful, coming from classical controllers, meaningful behavior. So we can actually say that there's a certain degree of safety that's coming from using prior knowledge to facilitate exploration. And then scalability. Essentially what we've done is we've decomposed this into skills, and we can use this to solve for each of those tasks that I talked about before. Each of these tasks, we actually don't have a classical controller that can perfectly solve them, right? But essentially, with a single skills module, we were able to solve all three of those tasks, right? So we're actually scaling hybrid learning across multiple tasks. We actually this is one thing that we haven't done, is to see how we can actually safely utilize this in a real world setting, and we leave that to future work. Maybe we can collect this data set from a real robot and build a skill space, and hopefully that might be able to facilitate learning, but that's something we will explore in future work. So, okay, in summary, this whole presentation, hopefully there's three key points that you got across. That reinforcement learning can greatly benefit from prior experience. Classical controllers present a rich source of prior experience for robotics, and we can address some of the key limitations faced by each controller by drawing on the strengths of the others. So it's not only from the RL perspective, it's also from the classical control perspective. Maybe reinforcement learning can help us solve some of the challenges that we face there. So in summary, we propose 4 different architectures. In the first one, we propose the combination of a residual policy and a classical controller together with an uncertainty-based switch for safe real-world deployment. Then we decided to use these policies, these classical controllers, to directly bias our exploration process in order to accelerate learning. And then we essentially incorporated the notion of uncertainty back into this training framework to allow for safe exploration in the training environment. And then finally, we decompose these controllers into a wide range of skills to facilitate learning across a diverse range of tasks. This work would not be possible without my amazing supervisor, Niko and Michael Mulford, who guided me, gave me amazing feedback all the time, brainstorming sessions. I really enjoyed this entire 3 years of my PhD, particularly because of you guys. Thanks to the ACRV, QCR, and Australian government for funding with my scholarships. Thank you to my amazing collaborators, Vibha, Ming, Jesse, Ben, Brendan. All of this work would not have been possible without any of you. And also my awesome colleagues, Timothy, Rob, Jordan, Tom Coppin, Doug Palmer, Jake Bruce, Serena, Lachlan, Andrew Melnick, Jad, and many, many more that I've met throughout the past 3 years. You guys have been awesome. And with that, thank you for listening. And are there any questions?